The first talk in this session is going to be given by Philippa Cowderoy on information-aware type systems and telescopic constraint trees. So take it away, Philippa.
Hi everyone. So you've just been told the title already. I better explain what I'm talking about. I got this idea I call information awareness, so I'm going to try and motivate that. Then I'm going to show you some of the tools I use to engage in it. And if I want going to ever give a talk, I'd have to show you something I can actually do. So I'll show you a style of type system, or at least a presentation style that uses them. Then, so the title doesn't make me a liar, I'll also introduce telescopic constraint trees. So, a while back I showed some of my work to my dad, and he couldn't follow the traditional application rule that was simply typed lambda calculus. He was just having trouble putting the two towers that I've got there together and realising, oh, they're the same thing. That's where the answer goes from. I showed him the version on the right, APIC, and he could immediately see how to implement that in Haskell. Now, Dad's not done masses of Haskell, he's done a little, but he can write Fortran in it. And the thing about APIC is that it shows us the information that the inference rule actually infers, that you've got this equality, and we can reason with it, so we can work out that TF must be a function that can take TP as a parameter. More generally, when I see a schematic variable somewhere, I look at it and I don't really know what it says. Is it using known information, or is it a pattern trying to find information out? Is that pattern linear, or is it non-linear? Have I got an implicit equality or something more subtle somewhere? Can I reduce it? Should I reduce it? Am I going to really regret it if I try reducing it? So I want to be more explicit about all of that, and information awareness is what I call the thing we get when we solve some of this problem. And I've got that explicit equality there. It's a constraint. It can help us do better, but using constraints on its own can't stop us from doing worse. Constraint systems in the limit are Turing complete. We can find a whole infinity of ways of confusing ourselves. So, tools for information awareness. The big new one for most people will be information effects, and I'll still be talking more about constraints. So information effects come from a paper called Information Effects by James and Sarbury. They were studying reversible programming. They built a combinator language where instead of functions, the combinators were isomorphisms. So everything was reversible by default. And then they realised they had a new kind of effect that happened if you let yourself break that rule. So you're doing isomorphic programming by default, and information effects are what happen when you stop doing that temporarily. I'm mostly going in one direction only, but that doesn't stop me from using the idea. It turns out to be kind of useful generally. Information effects are breaches of conservation of information in the same sense that we see in physics and quantum mechanics. When information is created, that's an information effect. The same when information is destroyed, and particularly pickily when information is duplicated. So, inference creates new information that's implied by the information we have, and that's the link with type systems. Constraints, I've kind of got this three-pronged view of. There's a syntactic aspect, they have static semantics, they have dynamic semantics. Now the syntax it really is just plain old syntax. It's what we wrote. It's information in the sense of Shannon. But the thing about Shannon is that bits are actually a really bad unit for precise accounting because, well, you've got that logarithm there and really you just want the algebra that's before it. The static semantics, what do we know holds if that constraint's satisfied? Possibly what do we know if the constraint can't be satisfied? the satisfaction predicate that says whether or not it's satisfied. And also, given the solvers we have available, what shapes of problem can we solve reliably? There's dynamic semantics. A constraint is part of a constraint problem. It's part of the process of solving that problem, which makes it a sub-process that can block on unknown information, or it can provide information. And those unknowns are represented by solver variables or meta-variables. Then the insight for this talk is constraints are kind of a good unit of information. So, on to information-aware type systems. My aims with the methods I use to produce them. I'll give you an example of a simply typed lambda calculus, and I'll talk kind of a bit about modes. And I might well take a question or two once I've dealt with the modes as well. So my aims are, I want to be able to see clearly where information is introduced and eliminated. I want to see the data flow. I want to see where I've got a choice about how data flows, whether it's in the design stage, looking at how I put the type system together, or when I'm implementing a type checker. I especially want to know that if I get different results in different directions. I'm going to use linear logic variables for the schema, so there's going to be one positive source and one negative sink occurrence for each variable. I'm going to use constraints because constraint generation is an information effect. They keep the data flow general, and as I've already talked about, they're a really flexible abstraction. And we're going to have explicit duplication because otherwise information effects don't work. You've shoved some of them under the carpet. That'll turn out to be a good thing. So for the simple typed lambda calculus, I'm going to need a simple type equality constraint. I'm going to need to ask if a given variable is bound to a given type in some context. I need to be able to say some context is what happens when you extend another context with some binding, and I'm going to need to duplicate contexts. Incidentally, I've got some red colouring on here, but so long if you're colourblind, you will be okay. There is no truly critical information contained in the colour. As a convention, I always write left equals right as if I'm assigning to the left-hand side, so patterns go on the left. The context constraints also end up encoding the structural rules. You can change the constraints and end up with a minimal linear system, for example. And then I've got a variable rule which uses the binding in context constraints. I've got a lambda rule where I have to build a context, check it out, and then construct a function type. I've got an application rule which needs to use context duplication, but I'm skipping past those a little bit into modes for the sake of time, and we'll go through those again. So modes tell us about which way data's flowing. They tell us about when we know enough to solve the constraint, and these things are possibly news to people. The general idea is that data goes positive to negative, and then constraints can fire when all their negative variables are known. There's a bunch of possible modes if you're new to this. We might know everything going in. Our type checker is just asking, does this program make any sense? We might not know the type and we'd be trying to synthesize it. We might not know the context and be trying to figure out the types of free variables. We might even not know the term and be doing proof search, and each of these modes can have its own implementation, what the logic programming crowd call a procedure. The other thing that's worth mentioning at this point is that the function arrow itself is an information effect. It doesn't show up anywhere in the source, and it is in our types. We keep inferring it, so it's information we create to describe our terms. And I give it two different modes based on how I expect the solver to handle equality constraints involving it, so that the left-hand side is still being assigned to. So a positive function arrow is acting as a constructor, and a negative one is acting as pattern matching. as it happens, introduction versus elimination. So, rules again. This time I'm going to make a little bit more effort to explain what's going on. So, we start off with a known context, which is going to flow up to that constraint there. We also know the variable we're starting with. Now that constraint's got all its negative variables filled in, it can fire and finally figure out the type, which it returns down at the bottom again. And all of this is because we're doing this for type synthesis. If we were looking for a free variable type system, the data would flow completely differently. The lambda rule is mostly more of the same. Our input term has two identifiable subterms, for example, so x flows up to here, whereas the initial context goes here, and at this point we now know enough to extend the context into a new one, introducing tau p. We don't know what tau p is going to be yet, but we know we want to use it, so we can talk about it now. Then our extended context flows down here, where we're about to type check the body of the lambda. That fires off and we get back a type. So now we know tau r, we can fill that in. We can fill that in here. We've got tau p with whatever we solved about it. From here, that fills in here. That equality constraint can fire, and now we know the type of the function represented by the lambda. Finally, the application rule. The very first thing that has to do, because we're going to check two subterms, is we have to duplicate the context. And one copy goes off to check the function. Ooh, this is going to be messy to highlight. The function. Apologies for this. Over here, and another copy down here. Oh good, I've got that one. Goes off to type check the parameter. The function goes off to where it's being checked, and the parameter to where it's being checked, and these things have completely separate names. You can see at a glance are separate in the same sense as separation logic. These two things can happen completely in parallel. So we figure out the function type, which flows down here, and we're about to pattern match against. We've got the parameter type, which flies in here, and from that, assuming that we got a function at all, we get the type of the result. And that's the application rule done. So this is the point where I said I'd take any questions initially, because I'm about to move on to telescopic constraint trees otherwise. Have we got anything?
Any questions for Philippa? Oops. Seeing if there's any online.
So, I mean, can I just a small clarification then? So it feels like I can essentially read these as an algorithm, right? It's like the program that I would write down. It's much more clear about how to trace things through constraint-wise. That's essentially
yes.
What. Yeah.
Yes, once we fix the mode, all the data flow becomes fixed, and then it becomes an algorithm. Before we did that, it's still a general type system.
but depending on what we fix the modes for the sort of the conclusion, that will change a lot the rest of the modes for the.
Yeah, the constraint solver may have to do some very different things. If we start out, for example, not knowing the context, and I make you walk the tree bottom up, well, I got thanks from Conor McBride a couple of years back for that one. Anything else, or shall I get on to the really fun party track?
Oh, I thought Tamo was asking a question, but he's on the phone.
Okay.
I think you can carry on.
Yeah, I was about to say, we'll call that his loss, I'm afraid. So, I've done with information-aware type systems, or rather I'm about to use them for something. Now I'm going to talk about telescopic constraint trees, what they are and do, how to build them, and some things to do with them. What is a telescopic constraint tree? Well, it's a tree. It's a refinement of the AST, in fact. It contains constraints, also metavariable binders. It's telescopic in de Brown's sense of telescope, which means it's built out of composable bits of context. And that's composable as in you can write your normal composition dot between bits of it. I'll also sometimes refer to telescopic constraint trees as TCTs for short. Now, what else is it? Well, it's a type checking problem and it's potentially in progress. You can start solving constraints and you don't suddenly invalidate the structure. It's generic. Anything you can sensibly do with the typing rules. If I've built a telescopic constraint tree properly, I can explain in terms of the tree as well. You can derive them directly from an information-aware type system, and they act as a scope-aware constraint store. Now, the simply typed lambda calculus doesn't really care about the scoping. You can just treat all the metavariables as global and run your occurs check and you're okay. You kind of start to care for Hindley-Milner so that you get your generalization in the right order. And when you get as far as dependent types, well, the first time I gave a talk on those, it was to the MSP group at Strathclyde, and I showed the slides to Conor McBride the night before. And I wasn't very clear about whether I was giving him the talk or talking to him about the talk, which led to a cry of, I was doing that 20 years ago. We managed to come to an agreement, which was that he had most certainly been implementing this 20 years ago, but I'd got a logical specification for what he'd been doing for 20 years ago now, and a way of deriving it. So I promise you I'm not just selling you the technology of 20 years ago today. What does it do? Well, it does what an ordinary type checker does, but a telescopic constraint tree does what an ordinary type checker does in time, and it does it in space instead. We do have to alter some of the constraints a bit, because if a constraint refers to the context, it's no good, because we're about to put it in a suspiciously context-like place. So the binding in context and the context extension constraints need reworking. I convert them into one thing which you can think of as a query, or in concurrent constraint programming terms, an ask constraint. What's x bound to here? Or is x bound to tau here? And the other into one which tells the solver they'd better become a binding of x to tau right here. So I call these situated constraints. Their meaning absolutely depends on where they are in the telescope. Incidentally, as a quick cheat, you can solve the tel constraint by just scrubbing out the exclamation mark. Suddenly you have an actual binding for x to tau exactly where it was. I've got the same type equality constraints, but I also need to be able to say I've got some metavariable tau I don't know about. And I also need to say I've got some meta-variable tau, and this is what I know so far. And if I can solve the two apart the way I can with the use of an equality sign or not there, I can ask, is this solved? And I can ask if it's part solved, if the head is solved. Then the really easy piece is that context duplications turn into tree branches. So we build a telescopic constraint tree by traversing the abstract syntax tree. We end up with what I'll call a TCT semantics, which, we've got our brackets around the term, but there's also a type parameter. The idea is to translate the term into a telescopic constraint tree in such a way that tau will become the result type, and to do this retaining all the information that is in the typing rules. And if we can do that, we're golden. So suppose we're doing synthesis again. We're going to need a starting tree just to get us going, which consists of the initial context, a binding for tau saying we don't know what it is yet, but we want to be able to use it in ways that say you know about it. And then we start building the TCT itself using our known term and our known about type meta variable. So tau's acting as a query variable in the sense you might talk about when you're working with databases or again in logic programming. Then with the var rule, we don't know the type yet, so it becomes, we translate the constraint at the top into the one at the bottom. And for subterms, the x we know about here becomes an x we're feeding in here. Then that constraint can fire and we get the tau we know back to return. Building the lambda rule is a bit more involved because there are variables that appear above the line that aren't below the line. So I need an existential binder for both of tau p and tau r. Once I've done that, the equality copies across directly, and then we know we're going to have to check the body. So I insist on the variable binding that corresponds to the top line here, happening down here, before building the tree that corresponds to type checking the body. Then the application rule is more of the same, completely, except that we finally have a duplication. So this duplication here splits the contexts. We've got one, which is, this is a pain to highlight. So let's highlight, it'll do the one for the parameter. That becomes the lower of the two branches there, and correspondingly the gamma f branch becomes the higher of the two. Otherwise, the equality constraint is there. We've once again copied out the binders for the variables that we haven't seen. So what can I do with it? Well, I can implement type checkers. I hope I could, or I'd have messed up pretty bad. We can instrument those checkers. Changes in the tree as we start solving constraints show the whole process of solving, including changes in scope, because sometimes we discover a meta variable is more global than we thought. Those changes preserve the AST structure, although we can miss it slightly. We don't have labels around it anymore. So we might want to put those back in as a little bit of an extra information. I think this might make a good UI for type level debugging. We can actually fuse the telescopic constraint tree away a lot of the times. If you suppose we've got a greedy solver for constraints, one that just solves them straight away the moment it sees that, and a tree generator that implements our semantics, we can pick the traversal strategy, and we can just fuse the tree generators as a producer to the greedy solver's consumer, and we'll get a traditional checker back. And top down, bottom up, we get our choice. There are times you can't do that. Those exceptions are interesting. Greed doesn't always work. And the reason Conor McBride has been doing this for 20 years is he works with type systems where they don't. We can find and explain some optimizations. One for Hindley and Milner, and I think this originally appeared in the Milton compiler. You can have an idea I'll call generalization depth. How many generalization constraints are there from where you are to the root of the tree? You can annotate every meta-variable binder with that depth, and then generalization constraints can generalize variables at the same depth, and generalization is now linear in type size instead of having to crawl back through the context and check for free variables. Anyway, that's pretty much me done. I mean, in summary, information effects, unsurprisingly, hopefully, track information well. Constraints are a good unit of information. Information-aware type systems exist, and there's an extended abstract you can read about them in again. Telescopic constraint trees can be derived from them. We can calculate trade-off and optimize from them. But if you remember one thing, telescopic constraint trees do in space what conventional checkers do in time. And that's it. Any more questions?
Thank you very much, Philippa. I guess we can all do a virtual hand clap now. Yep.
Thanks, everyone.
We seem to have a number of questions in Zulip. I'll start with Max. Can you give yours orally, Max?
Sure, yeah. Mine was just the first half of the talk, what you were doing looked a lot like the language in a paper by Uday Reddy, Typed Foundation for Directed Logic Programming. I don't know if you're aware of that paper.
It only rings the loosest of bells, so if you give me...
I linked it in the Zulip, so, but yeah.
Okay, cool. I won't have to Google it then. Thank you very much for the reference.
Okay. I guess let's take a silent question now. Ohad has rather a long one. I'll just read it out for now, and then we can parse it. So, I think we have a notation/description language for the various assumptions/conclusions on inference rules that describe to the constraint solver how to solve the constraints. We know that some collections of, I don't know why we've got collections of again, constraints cannot be effectively solved, perhaps not expressible in your description language. Do you have any proposals or suggestions for a programming language based on your constraint descriptions that gives the programmer tighter control over constraint solving?
I don't quite yet, but I do have an observation, which is that you can tighten modes to the point where they do something a bit like refinement types, so that you can start to have the skeleton of what the parameters are in there, and before you start filling in things as just positive or negative. And I think that's at least a starting point for describing what you can and can't solve, because it gives you a lot more room to say, I can manage that. I don't have anything for combinations of constraints yet. To be honest, I'm still thinking about how I'm going to actually build a general solver for these kinds of constraint problems. It's the kind of thinking where I think I know an answer and I should have coded this up by now, but I'll be coming back to that. I'm hoping I can perhaps get something from the session types community over time.
That sounds interesting. We have another silent question from Chris. I'm wondering if you can compare the approach you're describing here of modeling judgments to that of colored local type inference by Odersky et al. The latter involved coloring type constructors in order to solve subtyping constraints in type argument synthesis.
I don't think I've read that paper in so long that I honestly can't remember enough off the top of my head. What I can say is that you can quite reasonably write rules that are only supposed to be used in specific modes. And that means you can intentionally write two rules where you're still syntactically directed, but the moment you find out which mode you're solving, you now know which of the two you're working with. So, a little bit like some forms of bidirectional checking. I don't know how closely that ends up involved with the colouring, because it's been that long since I've seen it. So I'm open to an explanation if that's worth bouncing off me, but maybe afterwards.